Viewers to the online series of lectures for the course of Dynamical Systems. We first recall from previous lecture that if one let theta from R cross U to U to be a C1 dynamical system, in the open set U of R to the N with infinitesimal generator F from U to R to the N, then a fixed point of the flow theta, this map, is just a point in the open set U, which we denote by P star, such that the following relations hold. Theta of T comma P star should be just P star for any time in the set of real numbers. Or it can be rewritten as U P star evaluated at T should be the same as the point P star. It also holds for any time. This is our equation number 1. Okay. So this was the definition of a fixed point, right? The fixed point of the underlying flow of the C1 dynamical system. Now taking derivative on both sides of equation number 1, we obtain the following: U P star prime at T is equal to 0, since P star is just a point in U, and if you derive it with respect to time, you're going to get 0. Okay, and this holds for all time as well. But observe that since UP star evaluated at T is a solution to the system, the underlying system, dx by dt is equal to f of x, right? The underlying differential equation, this is the underlying differential equation, and UP star T solves this differential equation. One therefore must have, so in this differential equation, x is replaced with UP star T to obtain UP star prime T is equal to f of UP star of T, right? And that means, so, since P star is a fixed point of the flow, this has to be the same as, since UP star evaluated at T is the same as P star, it has to be equal to 0, right? Because UP star prime at T is equal to 0. Okay, so this is what we have. Solutions to equation of this form: f of P is equal to 0, are known as equilibrium points, points or singular points. Okay. So whenever you have this equation and any point that solves this equation is called an equilibrium point or a singular point. Okay. Therefore, we have just seen that fixed point of the dynamical system is an example of equilibrium point. Okay, let me erase this part. So we have just seen that fixed point of the dynamical system with infinitesimal generator f from u to r to the n is an example of equilibrium point, right? Point. But there can be equilibrium points that are not fixed point of the dynamical system, of course, right? Okay, there can be equilibrium points that are not fixed point of the dynamical system of the underlying dynamical system. A point P in the open set U, which is not a fixed point, of the system generated by F is called a regular point of F. Is called a regular point of F. So hence an equilibrium point can be a regular point of the generator as well. Hence an equilibrium point can be a regular point of F as well. Okay. Now, a solution to the system, a solution to the system dx over dt is equal to f of x, defined by 1, equation number 1, recall the fixed point thing. Okay, this was equation number 1. P star for all time in the set of real numbers. This was denoted by 1. Okay. So a solution to this system defined by this equation where P star is an element or a point or a vector in this open set U eventually satisfies, we have seen, eventually satisfies f of p star is equal to 0, right? And this solution is called an equilibrium solution, is called an equilibrium solution. Okay. So point to note is that up star t, up star at t, this guy is an equilibrium solution. Equilibrium solution. Okay. And p star, this guy, is fixed point, is a fixed point of the system, fixed point of the system that is an equilibrium point. Equilibrium point. Okay. So P star is an equilibrium point, whereas UP star at T is an equilibrium solution. Okay, so far so good. Now we turn our attention to limit sets. There is a new notion called limit sets. We will start with a motivating example, and then we'll define various kind of limit sets. Now, limit sets. So, recall the fifth example of lecture 3. Okay, it was a two-dimensional system. So the underlying system was a two-dimensional system where the flow was given by theta t pq is equal to e to the lambda t 1 t 0 1, this matrix times this vector pq, and this holds for all time in the set of real numbers, and all vector pq in R2. Okay, so this was the definition of the flow of example 5 in lecture 3. This we denote by equation number 2. Okay, and indeed I want you to verify that if you choose dx over dt to be equal to lambda x plus y, and dy by dt is equal to lambda y. Okay, so you see that this is nothing but our governing system. Dx over dt is equal to f of x, right? Because this is a vector equation. So in this case, f of xy is equal to lambda x plus y and lambda y, right? And I want you to verify that this thing is consistent with equation number 2, is consistent with the definition of the flow map given in equation number 2. What do you need to verify then? You need to verify that by verifying that f of x is this number lambda x plus y, it has to be the derivative of the first component of theta. So theta is a 2 times 1 matrix, that is a vector whose first component is e to the lambda t times p plus t times e to the lambda t q, right? So check that. If you derive this guy with respect to t and set t equal to 0, then you must get lambda x plus y. And f of y should be the same as lambda y, and lambda y has to be the same as d theta 2 txy, deriving it with respect to t and set t equal to 0. These need to hold, okay? Where theta t comma pq, this vector has two components, theta 1 t comma p comma q, theta 2 t comma p comma q. Okay, the first component of this vector is e to the lambda t times p plus t e to the lambda t times q. That's the first component. And the second component is e to the lambda t times q. This is our equation number 3. So you need to verify it. It's just straightforward to verify that this indeed holds. These things indeed hold. Okay. So I leave it with you. And these are going to be true for all t in R and all vectors pq in R2. Okay, good. Okay, let me erase these things. Now, thus, if this vector x of t, y of t is an element of the orbit of this vector pq, okay, we know the definition of orbit. So if this vector belongs to the orbit of pq, let me write it here, the orbit of pq, then it follows from the expression of this this vector theta, right? Let me write down the expression. Theta t comma pq was this vector, right? To the lambda t p plus t e to the lambda t q and e to the lambda t q. Okay, this is equation number 3. Okay, so if if this is this vector, then the norm of this vector x t y t is simply square root of, since we are dealing with Euclidean space, we have the usual Euclidean norm, and from this equation number 3, it's clear that this is going to be e to the lambda t times p plus t e to the lambda t q whole squared plus yt is this guy, e to the lambda t times q to the 2. Okay. All right. So let us expand it using the algebraic formulas, and we obtain e to the 2 lambda t p squared plus t squared e to the 2 lambda t q squared plus 2t e to the 2 lambda t pq plus e to the 2 lambda t q squared. Okay. Straightforward expansion using basic algebraic formula then leads us to the fact that the norm of this vector, the Euclidean norm of this vector xt yt, is equal to, well, the square of the norm, okay, is equal to e to the 2 lambda t. I am factoring out e to the 2 lambda t from here, p squared plus q squared okay, plus p squared q squared plus 2t pq. Okay, good. This is the norm squared. Now we are going to use the fact that p squared t squared minus 2pt q plus q squared is greater than or equal to 0. Okay, no matter what I choose for p and q, this is going to be positive or 0 for all t in R. Okay. And this leads us to the fact that p squared t squared plus q squared is greater than or equal to 2ptq, or in other words 2ptq is less than or equal to p squared t squared plus q squared. Okay, so from here we see that this expression is less than or equal to e to the 2 lambda t p squared plus q squared plus t squared q squared, and this guy is less than or equal to p squared t squared plus q squared. Okay, and now this is equal to e to the 2 lambda t p squared plus t squared q squared, then I write p squared t squared, and then I add these two q squares up to have 2q squared. Okay, and this is less than or equal to, so if this expression is less than or equal to e to the 2 lambda t times 2p square, of course, right? So I add p square to it, and that the resulting expression is greater than or equal to the older expression, right? Plus t square q square plus p squared t squared plus 2q squared. Okay, so far so good, and this can be factorized. P squared t squared plus 2 plus q squared t squared plus 2 yes, and this is going to be equal to e to the 2 lambda t square plus 2 times p square plus q square. Okay. Good. So let me erase this part. So we just found out that the norm of this vector xtyd belonging to the orbit of PQ is less than or equal to e to the lambda t square root of 2 plus t squared, the norm of this vector PQ, right, which is the square root of, which is the same as the square root of p square plus q square. Okay, and this is true for all t in the set of real numbers. This is going to be our equation number 4. Okay, good. Therefore, we immediately see that if our lambda, the parameter lambda, is strictly negative, we obtain from 4 that as t increases without any bound, the norm of this element of the orbit goes to 0, right? Since lambda is negative, right? So if t increases without any bound, if t goes to positive infinity, then this is extremely small and the norm is supposed to be less than or equal to 0, and the only way it can be true is that the norm is 0. And when the norm is 0, it means that the vector itself is a 0 vector, right? And we know that the norm of if the norm of a vector is 0, then it has to be the 0 vector, right? From which we conclude the following. If lambda is negative, strictly negative, then the limit of the following expression as t approaches infinity is the 0 vector, right? So since here theta t comma pq, this is nothing but x t y t, and we have seen that limit t approaching infinity x t y t, this vector goes to the 0 vector, right? Okay, so this is our result. So this result can be phrased as the following. We say that 0, 0, this vector on the right side, is an omega limit point write it like this: omega limit point of the orbit gamma pq. Okay, this is what we are going to write it. So this vector on the right side is the omega limit point, is an omega limit point, is not the omega limit point, because there can be more than one omega limit point. Okay, so the collection of all omega limit points will be called omega limit set. So now this, so here in this case 0, 0 is an omega limit point of this orbit going through PQ. This is what we say. Now we'll give the definition of limit sets. So this was a motivating example. Now let me give you the formal definition of limit sets. Definition of limit sets. Let theta from R cross U to U denote a dynamical system for an open set U of R to the n and let gamma p for p in U be an orbit of the point P, orbit of the point P under the flow of theta. Okay, which means that, so if you take theta t comma p, if you vary t in the set of real numbers R, you get all the points, and the collection of all those points is this set gamma p precisely, the orbit for the point P in U. So this is the scenario. Now the first definition is that of an omega limit point, it says that a point Q in the underlying open set U is said to be an omega limit point of gamma p, the orbit of p, if there exists a sequence of real numbers which we denote by Tm, such that Tm goes to positive infinity as m approaches infinity, and the following holds. The limit of the following expression as m approaches infinity is equal to q. Then we say that q is an omega limit point of the orbit gamma p. Okay, so this is the definition of omega limit point. Now I give you the definition of alpha limit point. It's the same thing except for the fact that now Tm will approach negative infinity as m approaches infinity. So the definition of alpha limit point a point Q in the open set U is said to be an alpha limit point of gamma p if there exists a sequence of real numbers Tm such that Tm approaches negative infinity as m approaches infinity, and the following limiting expression holds. Lim m tends to infinity, theta Tm comma p is going to be equal to q. The same thing as before. Okay. Only the fact that this time we are choosing the sequence of real numbers Tm such that Tm approaches negative infinity as m approaches infinity. That's the only difference between the alpha limit point and then omega limit point. Okay. Now the definition of omega limit set. Now that we know the definition of omega limit point, we can define omega limit set. Let me erase everything. Our next definition is that of an omega limit set. Okay, the set of all, we know the definition of omega limit points. So if I take the set of all omega limit points of the orbit gamma p, the orbit of the point P at U, right? The set of all omega limit points is called the omega limit set of gamma p, and is denoted by omega of gamma p. Okay. So similarly, one can define alpha limit set in the following: the set of all alpha limit points of the orbit gamma p is called the alpha limit set of gamma p, and is denoted by alpha of gamma p. Okay. All right. Now we'll study the example, the first example. Example 1. In detail, let theta, the flow map from R cross R2 to R2, be the dynamical system, given in equation number 2. Let me write it for you. Equation number 2. Yes. So the flow map was defined as follows: theta t pq was a vector in R2, was defined as e to the lambda t 1 t 0 1 pq. Okay. So this was the definition of the flow map. Let theta be the dynamical system given in this equation. This was equation number 2. Given in equation 2 corresponding to the two-dimensional system dx over dt is equal to lambda x plus y, and dy over dt is equal to lambda y, with lambda not equal to 0. How this two-dimensional system is related to this definition of the flow map has already been discussed earlier in this lecture, because you just need to use the definition of infinitesimal generators to find the infinitesimal generator in this case. Okay, for which the first component is lambda x plus y, and the second component is lambda y, that you can find using the definition of infinitesimal generator. So we verified it earlier in this lecture. Okay, So we have seen earlier that if lambda is strictly negative, so you see that, so this is the case, it cannot be equal to 0. So there are two possibilities. If one is it's positive, the other one is it's negative. So we have seen earlier that if lambda is strictly negative, then there is only one omega limit point, and for any orbit through PQ, for any orbit of the vector PQ, there is only one omega limit point, and that is the 0 vector. We have seen it earlier. For all PQ in R2, any vector, if I choose any vector from R2 and consider its orbit, then the omega limit point corresponding to that orbit has to be the 0 vector. That's what we have found earlier as a motivating example before defining the various limit sets. Okay. Now, for finding, so let us stop the first segment here. In the second segment, we'll start with the discussion with alpha limit sets, with the alpha limit set for this example. Okay. So thank you for attending the first segment.